Welcome to the Explainer. We've engineered these incredible systems that can write complex computer code, compose beautiful poetry, and even pass grueling medical exams. We interact with them literally every single day, just marveling at what they can do. But behind those glowing screens, there's a profound and honestly kind of unsettling reality. We don't actually know exactly how these systems work on the inside. We feed them massive amounts of data, they give us perfect answers back, but that space right in between, it's a dark, insanely complex labyrinth.
So this brings us to the core question driving our whole investigation today. Why are neural networks so notoriously difficult to interpret? As these artificial minds become, well, completely embedded in our society, the stakes of using technology that we fundamentally cannot reverse engineer are getting incredibly high. What actually happens when an opaque system makes a major mistake, or worse, behaves in a way we never ever intended?
Well, that's exactly what we're going to figure out. Today, we're undertaking a systematic investigation into the architecture of the artificial mind and exploring a groundbreaking new field of research that's finally allowing us to peek behind the curtain.
Section 1. The AI Black Box, Understanding the Challenge.
Now, before we can decode these systems, we really need to grasp what makes them so impenetrable in the first place. There are four major factors here. First up, modern networks contain millions, often billions of parameters. Trying to trace what just one single parameter is doing is a completely daunting task. Second, they use nonlinear activation functions. So unlike a simple equation where A predictably leads to B, these nonlinear boundaries create incredibly intricate, twisty patterns, making the decision pathways super complex. Third, we've got distributed representations. If you go looking for the specific folder where an AI stores its knowledge of, say, an apple, you're not going to find it. That concept is distributed, smeared across thousands of different neurons, all firing at once. And finally, just the sheer high dimensionality of all this data makes visualizing the space practically impossible for the human brain.
Section 2. Early Interpretability Methods. The first attempts at transparency.
Of course, researchers didn't just throw their hands up and quit when faced with this complexity. But, those earliest tools we had to look inside the black box were essentially just really educated guessing. We were relying heavily on visual intuition. Researchers used feature visualization to generate images that would highly activate certain neurons, basically trying to guess what the network was looking for. We used attribution methods, things like saliency maps and GradCam, to highlight exactly which parts of an image an AI was paying attention to during a decision. And we also tried concept-based explanations, like testing with concept activation vectors, just to see if we could somehow align human ideas with machine decisions.
A huge milestone from this era that you might actually remember is Google's Deep Dream, which came out back in 2015. It was this fascinating algorithm that took the patterns a network had learned and iteratively enhanced them in images, giving us those totally surreal, psychedelic visuals. But while Deep Dream looked amazing, it was really just surface level. These traditional methods were mostly focusing on correlation. They could show us what part of an image the AI was looking at, sure, but they totally failed to explain the underlying mechanics of how the AI actually processed it.
Section 3. The Mechanistic Interpretability Revolution. A paradigm shift in AI.
Because, let's face it, guessing just wasn't enough. Researchers started searching for a way to map the actual internal wiring. Okay, let's dive into this. Mechanistic interpretability, or MI. This is absolutely not about correlation. This is all about reverse engineering. Think about how software engineers can take a compiled binary computer program and painstakingly reverse engineer it to figure out its exact source code. Mechanistic interpretability applies that exact same rigorous causal logic to neural networks. It treats them not as mysterious black boxes, but as complex machines with real gears and levers that we could actually map out.
The term itself was coined by researcher Chris Olah, and his work represents a massive, game-changing shift. Instead of relying on those broad, gradient-based approaches like the saliency maps we just talked about, Olah and his peers decided to focus entirely on circuit analysis. They basically wanted to find the actual structural wiring of the artificial mind.
Section 4. Decoding Features and Circuits. The Building Blocks of AI.
So to actually map this wiring, we have to break the machine down into its most fundamental parts. The absolutely crucial point here is that this entire field hinges on two interdependent components: features and circuits. Features are the what. They are the specific properties the network has learned to recognize, maybe a low-level feature like a curved edge, or a high-level feature like a human face. Circuits, on the other hand, are the how. They're the functional, causal pathways, basically groups of neurons working together to process those features and make computations. Lower-level circuits detect the edges, and then they feed those into higher-level circuits that eventually identify the face. It's a perfectly hierarchical relationship.
But remember what we said earlier. These features are distributed across millions of parameters. So how on earth do we actually find them? Well, researchers at organizations like Anthropic are using a pretty brilliant tool called a sparse autoencoder. This is essentially a secondary model trained specifically to look at the massive, tangled web of activations inside a neural network and then untangle them. It forces all that chaotic data into sparse, isolated representations that humans like us can actually read and understand as distinct concepts.
And this whole effort is supported by something called the linear representation hypothesis. This proposes that despite the massive nonlinear complexity of the network as a whole, specific high-level concepts actually exist as simple, straight, linear directions in the network's activation space. For instance, in simple word embeddings, the relationship connecting a country to its capital is encoded in a very clear, measurable, linear direction. The idea is, if you can find that direction, you find the concept.
Section 5. Mechanistic versus traditional methods. Causality over correlation.
Let's put these two eras of research side by side to really see why MII is such a game changer. And this brilliantly illustrates the exact paradigm shift we're talking about. With traditional methods, we were essentially just observing behavior. The focus was entirely on correlation and surface-level input-output relationships. But with mechanistic interpretability, the focus is exclusively on causal chains. We aren't just asking what the model might be doing, we are mathematically proving the fundamental computational steps it is actually taking.
These foundational differences translate into massive, practical advantages for the field. First up, generalizability. Because MI uncovers core algorithms, these insights can often apply across totally different models. Second, scalability. Staring at saliency maps becomes totally useless for massive modern language models, but identifying fundamental computational principles? That scales up beautifully. And third, precision. MI provides rigorous, quantifiable explanations, and that is absolutely vital if we ever want to defend these models against things like adversarial attacks. You know, where bad actors trick the AI by exploiting its surface-level correlations?
Section 6. The future of AI safety, alignment, and roadblocks.
Look, if we can actually map the mind of an AI, the implications for human safety and society are just profound. But getting there, it is not going to be easy. The field is facing immense roadblocks right now. While the principles scale well in theory, manually applying these techniques to models with trillions of parameters is incredibly difficult. Researchers also have to figure out how to generalize these methods across vastly different network architectures. On top of that, bridging the gap between a single neuron firing and the model exhibiting high-level cognitive reasoning is what computer scientists call an NP-hard problem, meaning it is computationally monstrous. And we still lack standardized ways to evaluate if our interpretation is even completely correct in the first place.
Now, what's really interesting about all this is a phenomenon researchers discovered called superposition. This is perhaps the biggest puzzle in the entire field. It turns out, networks don't just store one concept per neuron. To save space, they literally cram multiple, overlapping, totally different features into the exact same neural activations. It's kind of like writing 3 completely different books on the exact same piece of paper, just overlapping the ink. Untangling that superposition to read the individual features is a massive, massive hurdle for researchers.
But honestly, despite these massive NP-hard challenges, the work absolutely has to continue. Mechanistic interpretability is without a doubt one of our best paths forward to ensuring that AI systems are not just highly capable, but transparent, safe, and truly aligned with human values. If we can map the exact circuit that leads an AI to behave maliciously or unsafely, we can physically intervene and change the wiring, rather than just crossing our fingers and hoping our training data was good enough. Which leaves us with a final, rather profound question. As these models grow exponentially larger and more complex every single year, will our tools for mechanistic interpretability even be able to keep up? Will we ever fully decode the artificial mind, or will the black box always retain some of its mystery? It's a question researchers are racing to answer every single day. Thanks so much for joining me for this explainer.